Hi guys, my name is Ryan Ferrero, and for my ECE 551 term project, I decided to develop the Wave Mode Simulator, or WMS. This simulator will allow the user to put in various conditions of some kind of membrane, and then MATLAB would be able to take that information and accurately plot the wave mode shape, helping everyone to visualize it in the end. So, for you continue on, our objectives of this project, or the WMS. So, the project aims to develop a graphics user interface, or GUI, that can accurately display a given wave mode shape of various oscillating membrane. Using the MATLAB compiler package, this program can also be ran as a standalone package that can run without the need to have MATLAB installed on the local machine, or I can make it into some kind of integrated MATLAB app package that runs directly through MATLAB. So this project hopes to provide visual representation of various wave modes of a rectangular membrane constrained by different boundary conditions, i.e. this be rigid or pressure release, and different sizes of the membrane via 3D MATLAB surface plots. These are offered as both a static image or animated. It also provides visual representation of various wave modes of a free circular membrane via 3D MATLAB surface plots, and these are also offered in both static and animated images. The program also outputs the corresponding mode frequency that causes that excitation and simulate the membrane with various mediums via an impedance adjuster. So what's the purpose? I hope that this project can be some kind of educational tool for engineers or anyone who's interested in the study of acoustics and electromagnetic waves. It's a very prominent field, so I think it's important that a lot of people understand how these waves vibrate within these different kinds of mediums. So I think this would be a great visual representation of various modes propagating through a waveguide. It could become a valuable educational tool to clear up any lingering confusion regarding the correct mode shapes of various boundary conditions. So I know personally I have trouble visualizing these waves without thinking about it. And while I have gained a much better understanding of the nature of how these waves propagate in various modes while taking this course, I know that that sort of intuition doesn't come naturally to a lot of people. It takes a lot of studying to understand it, and even then, it's hard to kind of see it. So hopefully, this could become some big educational tool one day that could help people like myself and like I'm sure many of us in the class have trouble seeing. So some background. What's a wave mode? Who here knows what a wave mode is? Raise your hand. Now I'm sure plenty of you guys just raised your hand just now, but there are tons of people who don't know what a wave mode is. So I think it's important that people understand just we all have some kind of common ground of what exactly is a wave mode, and that just being a wave mode or mode of vibration is a wave vibrating, be it in some distinct pattern, when a specific frequency is applied to a system or structure such as a membrane that can have several points of varying amplitude. These structures come in a variety of different shapes, such as rectangular, circular, that we have discussed during class. And we can see an example of a wave mode in the GIF down below over here. I think it helps a lot. So, this is an example of a rectangular membrane being excited in what appears to be the 1-1 mode, based on its half wavelength oscillation in both the X direction right here, if you look carefully, and if you look here, there's a half wavelength oscillation in the Y direction as well, or the Z direction, depending on what your axis is. It's not exactly clear here, but we get the general idea of it. So, and we have some other examples over here of a circular membrane and what appears to be, what is it? This would be the 2-1 mode. And then we have a rectangular membrane here as well. Yeah. So the wave equation. The wave equation acts as the basis of the entire project. It is from the two solutions that we see down here, both the Cartesian and the polar, that we can even plot via MATLAB. In the next slide, some pseudocode will be explained, detailing how the two solutions were used to accurately generate the shapes. And then with the user input for length, the corresponding kx and k values can also be determined, which helps to understand how the wave vibrates depending on the various different boundary conditions that the membrane is placed according to, and we can also calculate the frequency with all this information as well. So next, so we are a rectangular membrane, so our pseudocode for it. So I had developed some function called plot wave mode that took in the n, the m, and then the various boundary conditions and the user inputs for length as well. And basically all this code did was it checked the boundary condition for each one in some binary value, and depending on that binary combination of numbers, it would determine which mode it's in, or which not its mode, its solution. So it'd be sine here, cosine, cosine. It all depends on the boundary conditions of it. And then it would calculate the kx and ky values based on the lengths defined by the user, and the n and m values defined by the user. And it would spit out the wave mode shape and the frequency as well. And this process was modular, so that means that it can be repeated for everything. So this process keeps going on and on for all the combinations of possible boundary conditions, and we'll see that a little bit more in detail in the demo later on towards the end of this presentation. But as well, since it's modular, it's also easy to add additional boundary conditions such as mass loaded or anything else after that. But just setting those values to be something that's different than 0 or 1, and just having the program check if those boundary conditions are set to that. So I think it'd be a really easy implementation later on down the line if me or anyone else decides to do so. So for the circular membrane pseudocode, it's a little different than the other ones. It's not as modular as the previous code. It says the radius, it was defined within the function itself along with the phi plane. And then we use MATLAB's mesh grid to make a 3D surface of it. The KMN corresponds to the zeros of the first derivative of the Bessel function of the first kind, which if we scroll back a bit, has to do with this Bessel function right here and the Km in here. So there was a MATLAB file exchange that had a function that did this that I used, and I credit that towards the references at the end. It helps a lot, and I think you guys should check that out if you want to understand that a little bit better. It's a really long function. It's kind of complicated. It doesn't really fit within the time frame of this presentation, however. But I think it's something that's worth checking. It's a very useful function when trying to understand how these circular membranes oscillate. But in the end, we take this and then we just plug it into our wave solution here using MATLAB's Bessel J, our m value, and our zeros times the radius is along with our cosine of m times our phi plane. And then our max fj is just used for an animation loop. It's just for a for loop to gather the correct frames. So, the demo of our project. So, if we open up MATLAB here, we have the wave mode simulator. Right, it has two tabs, so rectangular and free on the top here. Starting with our rectangular membrane, we can select different boundary conditions from the top, right, bottom, and left here by just using a drop down to rigid or free. Our LX and LZ are auto set to 20 meters or 20 inches. Is 20 any unit, and that can be set by the user anytime. We also have the mode shapes here. We can set that up. We have our graph display, which can be either animated or static. Our sampling rate, which helps for animation to help smooth it out, and then our impedance adjuster here. Our mode frequency would come out on this end here, and it's a similar setup in the circular membrane side of it, where we choose our MN graph display, sample rate, impedance, and mode frequency comes out here. We just can't set the boundary conditions of the circular membrane. So if we do an example, we have rigid, we have all rigid across, and if we want, say, the 1-1 mode here, we have it animated, and we hit run. We'll see that it's coming. It animates up and down. I'm not too sure how the sampling rate is going to look on the video side of things, but it runs relatively well on my end of it. And then if we hit static and did, say, the 2-1 mode, we have a static image of it. And we can rotate this graph as well to get any better views of it. We can also save these images as well using the drop down toolbox over here. So I figured I should show you guys just different versions of how this works. So if I made the top and bottom free, and we just do a direct change from here, we can see that it starts messing up a lot of things, but we can see that this accurately displays what we think. You can see that it's rigid on the left and right side just because they're centered at 0 here, and that they're free because it oscillates fully over here. And you can see that this is a full wavelength, which corresponds to our n equals 2 here. So we see that this is accurately depicting what we set it to be. And if I change, say, maybe this to free, we'll see that the left, this one right here, will change. So we hit run. You can see that this one remains constant, and this one is now starting to oscillate in that sinusoidal way that we would expect. So it's a half wavelength here, because it corresponds to the 1 on this side. So yeah, if we go a little further, it can go kind of crazy. I think the highest I've done was 1010. So we'll see what that happens. It looks kind of gross when you don't adjust the size. So we hit, say, maybe 100 by 100. See how that looks. And we see it starts smoothing out a little bit better here, since that's entirely dependent on our X value, since you can't oscillate what you don't have. Yeah, you can see it ends up kind of gnarly, but if you keep changing that, and I put this back to a reasonable thing, maybe like the 3-2 mode. Yeah. So we can see that the rectangular membrane, it's acting as we would expect. It's not anything crazy. But if we animate this too, we'll see how that goes. We'll see that it's oscillating up and down as we would expect it to. And then the smoothest of this is depending on our sampling rate. Obviously, that's via Nyquist theorem. So this would, if I crank this up to 4,000 or so, we'll see. It gets a little smoother. I just don't know how it's going to show up on the actual video side of things. But you guys can feel free to check this out. I'll have links to the GitHub for this where you guys can install this into your MATLAB. If you guys want to check it out yourself, I think it helps to see it. And it's also just a nice tool to have in the long run. Yeah. And depending on the sampling rate also depends on how long the animation runs as well, as we see, as it hasn't stopped yet. But if we move on to the circular membrane side of things, we'll see that it's just a simpler setup as last time. So if we want, say, the 2-2 mode of it, and I'm just kind of static for now, and we hit run, we'll see we get a little surface plot of it. So, and we can see that the mode frequency does come out over here. It's 165.4 hertz. I didn't show it on this end, but this one would be 215.8 hertz here. Yeah. And this goes pretty crazy too. You can go up to like the 7.7, and it goes to there. It's a bit gnarly on that end, but I think it's nice to see it in this kind. Even though you'll probably never have a material that vibrates this acoustically, but I think it's nice to see what the extremes of the project can be. So if we put that, and let's just show a quick animation of, say, the 2-1 mode, right? So that's the Pringle mode, as I call it. And if we animate that, there we go. So yeah. Right, and moving on back to the presentation. So what could have been? There are some things in this project that I wasn't able to exactly finish. So I didn't show the impedance adjuster too much because I didn't really change it as well. It just changed the amplitude. It should change the frequency of the mode as well, because obviously if you have a higher impedance, the membrane is gonna have a harder time oscillating. So I'd imagine that the frequency would be adjusting based on that as well. I just hadn't had the time to finish that. I would also like the ability to change the boundary conditions of the circular membrane. As of right now, we know it's just free on all sides, on its outer ring. I would like it to be able to be rigid or maybe mass loaded as well. Again, I just didn't really have the time in the long run for that. I think something that'd be really cool is the ability to change where the excitation is occurring. So maybe it's occurring right in the middle of the membrane, or on the side, or around the right side, or around the left side, or anywhere in between some kind of grid system. That was just a little too complex for the scope of this project, given the time that we had. But I think in the long run that'd be really cool, and it could help a lot in understanding how these waves actually vibrate within these membranes. I'd also like to have consideration for other types of boundary conditions, such as the mass loaded, because again, it's just the rigid and pressure release. It's just the basic ones we covered in class, and then some kind of animation speed adjuster to help how fast or smooth it goes in real time. Okay. Takeaways: over the duration of this project, I've been able to apply the concept of wave modes in different scenarios, effectively grow my understanding of the topic as a whole, understand the effects of different mediums play on a membrane vibrating in various mode shapes, gain a better intuition of how modes are generated due to visual exposure of these modes, explore how different boundary conditions play a major role in a membrane's ability to oscillate outside the scenarios presented within class. Obviously, we went through some boundary conditions that we didn't see in class, so it's nice to see how different boundary conditions affect these waves. And then develop a tool. I was able to develop a tool that can ultimately lead others to have these same takeaways listed here. I hope you guys are able to learn as much as I did through this project. I hope you guys are able to check out the project as well and test around with it and see what I may have did wrong on it in the long run of things. But yeah, thank you for you guys' time, and I hope you guys have a great rest of your semester. I'll see you guys later.